Great. Welcome everybody to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension Wisconsin 4-H. And on behalf of those folks and our other co-organizers, the Wisconsin Alumni Association, PBS Wisconsin, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, I'm delighted to welcome Johanna Osterwijk from Horticulture and Extension. Tonight she's going to talk about vertical agriculture, vertical farming, and now I get to ask her the 5 questions. Johanna, where were you born?
I was born right here in Madison, Wisconsin.
Native. And where'd you go to high school?
I went to high school at Abundant Life Christian School.
And then where'd you go for your undergrad, and what did you study?
I went to UW-Madison for my undergrad and studied horticulture.
There's a theme going on here. And do you have any advanced degrees?
I have a master's degree in life sciences communication from UW-Madison.
Way to go. And what's your favorite institution of higher education? Never mind. This is a pretty cool subject for me. I took horticulture and general ag in high school. We didn't have a greenhouse to begin with. Everything we grew had to be on racks like this, indoors. And to see how the field has advanced over the last 50 years is pretty amazing. It's not an elixir, it's not a fixer. We're going to hear about that tonight. But it's going to be great to hear about how we can grow plants indoors with special lights and some pretty great historical milestones out of UW-Madison. Would you please join me in welcoming Johanna Osterwijk to Wednesday Night at the Lab?
Thank you for that introduction, Tom. And thank you all for coming out tonight. As I just told Tom, I started here as an undergrad in horticulture, and unlike many undergrads, I knew I wanted to study horticulture right at the beginning. And by the end of my freshman year, I actually had a job in the campus greenhouses, and I really never looked back. That was very clearly what I wanted to do and where I wanted to be. I gotta say that my favorite thing about horticulture is how integrated it is as a field, how it pulls from so many other disciplines. It is application of not just botany, but also physics and chemistry. I teach a class in controlled environment food production, and I teach a class in greenhouse cultivation. I was talking with my students this morning about fertilizers. You can't talk about fertilizers, plant nutrition, soils without talking about chemistry. So all of those things come together, and then just greenhouses are the kiss on top of that with adding in engineering and mechanics, plumbing and electrical. So all of those things together, because I get to be not just a gardener, but also a plumber and a mechanic, depending on what we're doing today, which with my students working for me in the greenhouse included hose repair, because I'm not going to call the facilities plumbers if I just need to fix something like that. So today I'm going to talk to you about vertical agriculture. We hear a lot in the news, a lot of promotional material, and I want to talk about what it is that they promise, what they're saying we can get. And really it kind of comes down to fresh local food using less resources and less land. So my talk tonight is going to go through all of those promises and see how they really do add up. And it very much is in the numbers. But this is the goal and the promise, and it's a worthwhile goal. And I have experienced myself knowing just how important it is and how good it feels to have access to fresh food. A while back, I bought a sandwich for lunch, like one of many made on this campus. Gets made in a central kitchen from lettuce that has probably been trucked across the country, sits in a cooler for a couple of days, and then it comes to me. And I was so disappointed when I opened this thing up. I was going to add mustard. So I looked at it and I went, oh man. But I tell my kids, you get what you get, right?
Yeah.
Why am I complaining? And then I remembered, I'm a greenhouse manager, and I am literally teaching my students how to grow lettuce. A much more satisfying sandwich was a few steps away. That is really the promise that vertical agriculture offers us. It says, we are going to bring the produce right to your door. no loss of nutrients, no loss of quality. But they also promise to do it with minimal added inputs, is sort of the way that they're saying it. And I want to walk you through why that's not really true. But the greenhouse that I manage is the D.C. Smith Instructional Greenhouse. We are the teaching greenhouse for the College of Agriculture here at UW. And as you can see, I was teaching my students how to grow lettuce. Now, to be honest, this is not vertical agriculture, which is the topic of my talk, but I first want to bring up a couple of definitions. Controlled environment agriculture, which is what I teach and specialize in, is, I'm going to split it up into two different areas. Greenhouses, transparent structures, so we use natural light to provide most of the energy for plant growth, but they may have supplemental light as well. This time of year, we kind of need that. As you were all trickling in, the light was fading from the sky, and it's only 7 o'clock at night. Usually, though, greenhouses will have a single layer of crops, as you see there, with the students pulling them out. A plant factory, on the other hand, is an enclosed space. It's an opaque building, sometimes a warehouse, sometimes built specifically for that purpose, but no natural light. So all of the plant energy has to come from supplemental light. The crops in there may be in a single layer, but they may also be in multiple layers. So controlled environment agriculture itself actually offers a lot to fresh local produce. Controlled environment agriculture offers to increase and does increase capacity for production, primarily by increasing the amount of time that you can grow. You can grow every day of the year except May to September here in Wisconsin. By increasing that available cropping time, it actually multiplies the available space. And greenhouses are bigger on the inside than the square foot, the footprint actually implies. Controlled environment agriculture also increases production capacity by using wasted space. Also here on the UW campus, this is the housing greenhouse on top of the Leopold dorm. Students in the greenhouse residential learning community sign up for that specific dormitory and use that greenhouse as part of their curriculum, part of their cooperative living. And they grow vegetable transplants that are later put into the student organic farm that's thriving out at Eagle Heights, right next to the community gardens and the BioCore Prairie. Controlled environment agriculture, however, in all these forms requires considerable resources. The structure itself, the energy, equipment, the labor, often the hydroponic systems, all are heavy resource users. But you multiply the capacity by the extra time and space that you get by growing inside. Vertical agriculture increases production capacity as well by increasing space efficiency. So we take that footprint and we don't just grow through the whole year, but we grow in multiple layers potentially within, or multiple layers within that space. So crops are grown vertically or in layers, as you see here, and they're grown using space-saving technology, sometimes with tiers or layers, shelves, sometimes carousels that literally bring the plants to the workers so that space is not wasted for aisles, just like the libraries at Memorial Library carousels at Memorial Library. You put the aisle where you want it, and you have much more space for your books. Usually, though, vertical agriculture is combined with controlled environment agriculture. So that's why I wanted to give you a background on controlled environmental agriculture first, because we'll talk specifically about vertical agriculture in both greenhouses and plant factories. I'm trying not to use the term vertical farm because vertical farm is a little bit ambiguous. People often use it just to mean a plant factory, but then they'll also call something that's really a greenhouse a vertical farm. So I'm trying to give you three distinctions as we talk about this. Vertical agriculture is growing up, and it can be done in either of those two options. In a greenhouse where we use solar radiation supplemented with electrical light, or in a plant factory where the plants rely entirely on supplemental radiation. You're going to hear me talk about light a whole lot, though, because we can grow layers of crops one on top of each other, but plants have to have light. And it's only that we can make electric light that makes this possible. We've got these trays growing under LEDs. The ones on the other side are fluorescents. So there are a number of different lighting fixtures that are used in both greenhouses and in vertical farms. But first of all, now that we've got the definitions out of the way, let's talk about light, because light is really the critical factor that involves growing indoors. No plant's natural habitat is inside. Our houseplants, which many of you probably have, do well in our homes, but they are pre-selected as low-light plants. We take the plants that are our typical houseplants from the understory of tropical rainforests, where light levels are already very low. It's important to recognize that humans and plants perceive light in different ways. Light is important for us to see. We want to know how brilliant the light is. Can I look at my newspaper and read it? For plants, it is their energy. Most crop plants, vegetables, grains, tubers, they are highlight plants. Our grains come from savannas and prairies. Our root crops need a long time to grow, to soak in that sunlight, to produce those thick, starchy roots that give us back the light energy in chemical calories and starches. Plants need light. How much does light matter? Well, I am growing this experiment in the greenhouse right now to demonstrate this to my students, so I brought you some pictures. Here we have plants on the top growing with supplemental light. So I have an extra light fixture over those, and they have what's roughly the equivalent of 350 watts per meter squared. Now, if you have done light measurements, you might be going, well, where are my foot candles? Where are my lumens? Lumens are for looking at. Lumens are what we are interested in knowing. It's an architectural term. Watts are energy, and plants need light for energy. So it's a little hard to see these shaded ones. That's a 50% shade cloth. Now this is added light. This is taking away the ambient light in the greenhouse. And here's a better picture of what those two plants look like. These are radishes. The one on the right has a radish. It has taken that solar energy, converted it through photosynthesis into the chemical energy that is making that thick, fleshy root right there. The other one is closer to what we consider to be the compensation point. It has just enough energy to keep going, but not more to store anything away, to grow a couple of extra bigger leaves. So this is the distinction. This is why plants need light, and I need to emphasize it because without light, why are we bothering? I guess I could grow these probably in my living room, but if the point is to get that radish, to get that food crop, we have to provide supplemental light. And plant factories rely entirely on supplemental light. Even in the greenhouse, we don't get all of the natural solar radiation. We will have to supplement somewhat. So outdoor, I took these measurements this afternoon at noon. We had 440 watts per meter squared. In the greenhouse, we lost almost half of that just because of the glazing, the structural shadows, and depending on where you are in the greenhouse, if you're under a shadow, it might be less, but I tried to find a sunny spot. Your typical office building, and this bears out with what this space was like before they turned down the lights, is about 2. In foot candles, it's like 50 foot candles. Now this is sun in October. Sun in summer, up over 1,000 watts per meter squared. But plants don't need all of that light, so we don't have to light to that high of an intensity, but it is important. It is essential for good crop growth, and when we talk about energy costs for indoor cultivation, it can be up to 50% of the energy use in an indoor controlled environment facility. Half of it's going to go to light. These two trays were planted at the same time with the same crops. One was under cover there on the right. The one on the left had access to light for all of its growth. Without enough light, our crops won't succeed. And this has been a problem, well, for a long, long time. You can't make sunshine. This is a quote from the American florist 130 some years ago. However, right about this time, there was a very interesting invention, the Edison light bulb. Actually a few years earlier, but it took a little while to get the electrical infrastructure so that they were readily available. However, even growers knew even then that without light, you were not going to grow crops. Liberty Hyde Bailey in 1891 did the first experiments growing plants under those electric lights. He's a professor at Cornell and incidentally a founder of the extension and 4-H systems as we know them. Sometimes called the founder of modern American agriculture. But he was very clear that yes, it was possible and it did improve crop growth to give them that extra energy, but not economically feasible for food crops. So he's like, yeah, we can do it, but I don't recommend it. This has been a problem for growers for quite some time. Tom mentioned at the beginning of the hour that they'll be putting in a new memorial to a famous Wisconsin innovation, warfarin, which will be, as he said, next week's topic. There are memorials like that scattered all across campus. This one happens to be outside the greenhouse that I manage. You can see the D.C. Smith greenhouse there in the back, and it's actually right in front of the Plant Sciences building on Linden Drive. I would like to see another one of these put up. I'm glad they're doing more for warfarin, but I would like to see advancements in indoor agriculture celebrated just like this. LED grow lights and UW-Madison. So I pulled up information from the US Patent Office. The first patent for light-emitting diode grow lights was awarded to researchers through the Wisconsin Center for Space Automation and Robotics back in 1989. Since this was submitted in late '88, it took until the next year to get that. But the inventors all worked for the Wisconsin Center for Space Automation and Robotics. Their research was funded by NASA, who had an ongoing collaboration with UW researchers working on growing crops in space. Because they know that if we are going to go any further away than we have, we are going to need to support ourselves. So NASA is very interested in growing plants, growing crops, and feeding potential colonists as well as astronauts. Potatoes were some of the first crops grown in space. Spuds in Space was the fun name for that project. But the Wisconsin Fast Plants, used in high schools and universities throughout the US, but actually bred for fast response experiments that could be done in the terms of a space mission. Light-emitting diodes are what we call solid-state lighting. It means that unlike the incandescent bulbs that we're mostly moving away from, or that are with a burning filament gives us light intensity, or the fluorescent bulbs that cause gases to glow, these ones are an electric circuit. And it is the glow from the electric circuit, the electricity coursing through that, that produces the radiant light and the radiant energy. For our purposes, this technology was game-changing. LEDs were not new, but this application was, and that's what that patent is about. And now we can make sunlight, and we can make it more efficiently than ever before. Even in the patent approval, it says that this electrical conversion efficiency of electrical energy to radiant energy was more efficient than any they had at the time for plant lighting. How efficient was it? Well, here is a graph demonstrating the changes in efficiency over the last 20 years in common grow lights used in controlled environment agriculture. So back around 2000, you can see this black line is high-pressure sodium fixtures. These have, for 20-some, 30-some years, been the workhorses for controlled environment facilities. When the greenhouse that I managed was dedicated in 1997, these were the lights that they installed. They were the best that they had to offer. At that time, this, in the upper graph, the red and the blue line, you can see they were not as efficient at converting that electrical energy into radiant output. That's the photosynthetic efficacy, meaning joules in and micromoles per joule out. Micromole being the way that one of the ways that we measure light, in addition to watts per meter squared. Here we are now in the early 2020s. Now we are seeing those LED grow fixtures having surpassed the efficiency of the typical high-pressure sodium lights, and now they are almost the industry standard. It's actually getting hard to find replacements or repair parts for my HPS fixtures. And this summer, with funds from donors to our 25th anniversary campaign for the DC Smith Greenhouse and a grant from the UW Green Fund for Sustainability, we have replaced the high-pressure sodium lights in more than half of our grow rooms with LED fixtures. So how is that going to compare for us energetically? I've got an example that's a case study that was done actually by the Sacramento Municipal District. They were interested in seeing how cannabis production would work. This is an example, is a plant factory, so it's all sole source lighting, or all supplemental lighting. The picture on the left is high pressure sodium, the picture on the right is LED. From the introduction to their article, they knew already that lighting was a huge cost. As I said, up to 50% of the expense, of the energy cost of a growing facility is going to be lights. 550 kilowatts. That's just the immediate draw. That's not kilowatts per hour, that's kilowatts. That is the draw to keep your lights on. A typical office space of the same size, 8 kilowatts for a 10,000 square foot office space compared to a 10,000 square foot grow room, in this case for cannabis flowering. Bring that into homeowner terms, it means about the same as 7 refrigerators running to support just one cannabis plant. It is a lot of light energy. But as we saw with the radishes, without that energy, it's a very poor meal for the plant. So finding energy efficient options is essential if we're going to grow indoors. So lighting is in yellow, this top bar here. Again, these are data from this same study. Again, you can see in the pie chart, 40% of the high pressure sodium total energy is from the lights. That was lessened with the LED. They did 2 repetitions of the LED fixture room, and in doing so saved 18 and 25% energy savings subsequently. Gave them about a 3.5-year payback. So LED fixtures are more expensive. As we know, our LED bulbs are more expensive than the old style used to be. But significant energy savings, but still 30,000 kilowatts for a 2-month lighting cycle. So this was just during the flowering cycle of these crops, which is just 2 months of their life cycle. And this was for a grow room with a 384 square feet of canopy, so roughly 2.5 times the size of one of my houses in the DC Smith greenhouse. So not a very large space. But LEDs make it cheaper to light indoor crops, but we are still using energy that maybe we don't need to. This is an example from a plant factory. How do you make all of that light energy? For a plant factory, it all comes from light bulbs. It is all electrically produced. Most of that electricity is going to come from the power plant and potentially from a fossil fuel source. all of this is energy conversion. The plant is going to photosynthesize and convert that electrical energy into sugars and starches, but that electrical energy used to be fossil fuels. That fossil fuel energy was laid down millennia ago by not actually dinosaurs, probably something similar to an algae or some other microorganism. And those organisms got their light initially from solar. Why not just go straight to the source? So I want to do a comparison, or show you a comparison now, of the difference in energy costs between a greenhouse and a plant factory. So the plant factory we just looked at, all solar source lighting. A greenhouse relies primarily on natural solar radiation. The buildings themselves are less heat efficient though, so your heat costs go up. But Harbeck and Albright did a study on, this was modeling energy efficiency. So the last one was a case study that was actually done in California. This was an energy model. So they posited four scenarios, looking at different places around the US. Since greenhouses, the heating costs were going to vary depending on where you were, but the lighting costs as well. So they looked at the locations and climate zones for actually quite a few different scenarios. We're going to narrow this down to just what I'm interested in. So they had 2 plant factories and 2 greenhouses at each of 4 locations. And this bar is basically split up by light on the left, heat in the middle, and ventilation and cooling costs to the far right. Let's narrow this down a little bit. They did a repetition of this in Minnesota using Minneapolis, Minnesota climate considerations, pretty close to us, so I thought I would pull this one out to take a look at. So the top 2 bars are a plant factory. As you can see, light, almost 50% of the energy cost. The bottom 2 bars are 2 greenhouse scenarios, and the difference has to do with winter ventilation. Did they use fresh air from outside to ventilate and dehumidify the space, or did they keep it buttoned up and just deal with the extra humidity in different ways? So these are the 4 examples. A well-insulated warehouse with supplemental light. PF2 is actually the same, but had an extra energy efficiency algorithm, so they added some extra controllers to try and squeeze out what they could. And then, as I said, the greenhouse one, supplemental light when needed. And you know what? Minnesota does need it, just like we do. And then a greenhouse with winter ventilation. You can see the light intensity is the same, but the heat calculations are far different. However, the cost to ventilate and cool a greenhouse, you can barely see that little sliver on the end, whereas you do spend a considerable amount of energy cooling and ventilating a plant factory, which might surprise you. You think, oh, it's all buttoned up, it's cool. All of the equipment puts out a lot of heat that you need to get rid of, and all of those plants pump a lot of water into the air and you need to dehumidify. So there are additional cooling and heating and ventilating costs to a plant factory that you might not consider for a typical structure or building. So what came up of this? So you can see greenhouse costs. I'm going to go back. So this is in Minneapolis. Clearly, the greenhouse has a energy efficiency improvement over the cost of a plant factory, but most of that really is in light savings. So saving money on energy production. But location does matter. What if we weren't growing in the cold and frozen north? What about someplace that has lots of light energy and maybe doesn't need as much heating energy? So here we have the plant factory again, but in Phoenix, Arizona. The plant factory, still going to have to light it. The greenhouses, though, a little bit of supplemental light later in the winter, but far less light, heating, and cooling costs overall. So location really does matter. A plant factory might make sense for Minnesota or Wisconsin, but rarely in a sun-rich place like Arizona. So this is a question that I ask my students, and I actually give them this data. What makes sense? Do you want to heat a greenhouse or light an indoor farm? There's a little bit of variation in energy cost. So the price per kilowatt hour for energy in Arizona is a little bit less than it is in Wisconsin. But the total cost is still, in the hundreds of thousands of dollars. This is a total energy cost, light, heat, and ventilation, for a plant factory on the top, and then for a greenhouse lower down. But you can see how much it increases as you leave the sunny, warm climate and go to the cold, dark one. So we use these numbers to evaluate and think about, yeah, we can light an indoor farm, but is it the best use of our resources and of our capacity? So LED lighting and controlled environment agriculture is really a talk in itself, and you're probably wondering, when is she going to get to vertical farms? I have one more thing to tell you about light-emitting diode and LED grow lights. What I've shown you so far is mostly single-layer cultivation, but what is special and specific to vertical farms is that multi-layer cropping. LEDs make vertical farms possible, not just because of light efficiency, but also because of heat. That heating, ventilating, and air conditioning, I'm going back to that Sacramento study, that case study. Overall energy consumption was reduced, not just lighting. The choice of LED light fixtures also reduced the cooling and dehumidification cost and the electrical reheat energy. Electrical reheat is part of the dehumidification process. In order to get that extra water out of the air, they actually cool it further than it needs to be cooled and then reheat it just to change the relative humidity. So you can condense a lot of the condensers will get the excess water out of the air, but that means cooling the air and then reheating it, and that is an energy cost. So LED light fixtures, the blue line is the HPS fixture, and the orange and amber lines are the LED fixtures. So the LED rooms needed less energy for heating and for cooling, as well as for lighting. Interestingly enough, it was fan power circulating the air was the only place where the LED rooms were outperformed by the high-pressure sodium, the HPS rooms. One of the reasons for this is heat production from lighting fixtures. Those high-pressure sodium fixtures, you look at that picture on the left, you can just feel the difference. Walk in there like, oh, it's going to be hot. That cool white light, well, sometimes you see the purple and blue one, but this particular installation used the daylight color of LEDs. But lights produce heat. High-pressure sodium fixtures in particular radiate infrared energy. One of the reasons that LEDs are more energy efficient is that the light, the radiant energy that they are producing, is more specific to plant wavelengths, the reds and the blues, that plants like better. There is a lot of waste radiation, including infrared radiation, in a fixture like a high-pressure sodium lamp or an incandescent lamp. We all know you can warm your hands around an incandescent lamp in a way that you can't around an LED. LEDs don't radiate infrared in that way. They do warm up, but that heat is actually conductive. It is within that chipboard or that circuit, and it gets conducted and kind of goes out the back or up the top as heat rises. So it is not radiating it and producing it with the visible light energy. LEDs produce light in select wavelengths. We can actually fine-tune them to those different colors. Specifically, we like the reds and the blues that plants need, but we can choose them for any individual color we want. This is what makes stacking plants possible. The infrared radiation coming out of this high-pressure sodium fixture means that you must keep it feet to yards away from the plant canopy. Too close and it will burn the plants. LEDs, on the other hand, can be kept within inches of the fixtures. Now, if you're worried about the heat that's produced by that chipboard, that little bit of heat that's going up, plants actually really love it when you keep their roots warm. You might have a heat mat for germinating seeds or for propagating or just for keeping your plants warm. So honestly, this is a bonus. Plants like having their roots warm. But the key point here is that because LEDs don't radiate heat, they don't warm the crop as they light it, you can place them close to the plants, mere inches rather than yards above. And that means 8 to 10 layers of crops instead of one in a typical structure. That means that we can do vertical agriculture in plant factories or in greenhouses. But that's the benefit of vertical ag, growing multiple crops in one place at the same time. I should point out, I realize I've got logos and brands on some of these. I'm not promoting those particular brands. They're for illustrative purposes only. But vertical ag stacks plants. It makes a more efficient use of the available space. We do this by growing up instead of out. This particular greenhouse says that their vertical ag technology fits 10 acres of growing space on a footprint of 1/10 of an acre of land. They use trellises to string plants up tall. They also use a carousel system, as I described. It removes the aisles but moves the plants to get them closer to the workers when they are needed, but then you don't have to waste aisle space. You can keep that space growing for the plants. The greenhouse that I manage, we are practicing vertical agriculture right now with my controlled environment food production students. Here we have cucumbers growing. This is actually last spring's production, but you can see we've got some fruit there on the vines. So greenhouses, as well as plant factories, can be vertical farms. You're probably not going to do the close-spaced shelving, but they can be convinced to grow up instead of out with tiers, trellises, carousels like the one I described before, or green walls. This particular installation, all of these 8 cucumber plants are growing in 2 slabs on the floor. If you do any gardening, you know that cucumbers take a lot of space. The general recommendation is 8 square feet of space for 1 cucumber plant. These slabs, I did the calculation, they're about 8 inches by 40 inches. That's like, altogether between the 2 slabs, 5.5 square feet of growing space. I have 8 plants growing in less than the space that I would need for 1 plant if I just let it sprawl on the ground. This is something that you can do in your own home garden, just with a trellis and some string, increasing the space efficiency of your own garden. But there are additional costs. The cost for the labor to do the training and the pruning, and the cost of the materials to train them up as well. However, the promise of that vertical infrastructure is very great. This is a 2014 model that was done by a German researcher. So they posited a vertical farm, roughly, 0.93 hectares, so just about 2.5 acres, the size of a city block. But they think that they can grow all of these different crops in that space and provide 15,000 people with 2,000 calories a day. So they're offering to grow potatoes. It would also include an aquaculture, aquaponics system. Down in the basement would be 3 floors of aquaponics. Some space given to the environmental controls, but of the 37 floors in this space, they are suggesting that 25 of them would be used to grow crops, giving you a total increase in production of 516 times what you would in that 0.93 hectares of space on the ground. I have to say, this is a bit excessive. numbers look great in models. I have yet to see anybody come near to pulling this off. But it's a nice thought experiment. Something a little bit more realistic, but typical of indoor farms, increased yield along the order of 40 times field production. Now this is not just the vertical technology, but also the extended cropping time. So here, Eden Green technology, 500 tons of leafy greens in an acre and a half of greenhouse. Just for kicks, I decided I wanted to run the numbers on this one. A lettuce field averages about 15 tons per acre, so definitely a large increase. So 22.5 tons in 1.5 acres, but if you multiply that times 40, it's 900 tons. So I don't know, I'd like to see their numbers on that, because that's not 40 times field production. So maybe I'm missing something. It does say leafy greens, and I took lettuce as my exhibitor. I mean, still significantly better than you are doing in field production. But I do take a lot of these vertical farm promises with a grain of salt. So I want to show you again this slide that I started with. Let's look at each of these items. We've really already looked at that middle one, but can you really grow with 95% less water than typical outdoor farms? So do we get those increased yield and decreased resource use? Here was a model for annual water use, liters per kilogram, still of lettuce, but grown in Arizona using hydroponic versus conventional methods. So if you grow hydroponically in a greenhouse versus if you grow in the field. And here you see, honestly, roughly a 95% decrease. On the left is the hydroponic water use, on the right is the conventional water use. Hydroponic systems that recirculate water, the only water that is lost is into the body of the plants through transpiration, are extremely water conserving. So this is really something that controlled environment agriculture and vertical farms do deliver on very clearly. Looking at the, looking at the next item, we did talk about how they improve upon land up to 97%. I'm not really sure. I guess if you have a really tall building, potentially yes, but you'd have to grow up a lot. So the final one, less energy, food miles, and waste. And here I am very skeptical. Less energy? If you are growing indoors at all, your energy and resource costs are going to increase. As far as food miles, yes, you can grow right where your consumers are. That was the point of that Berlin model. They wanted to say, okay, can we feed 15,000 people who live around this 1 square block? So yes, you could potentially grow in the middle of the city, right where the people are. But if your argument for growing locally is to reduce food miles, we usually talk about reducing food miles to reduce carbon dioxide emissions. What is the difference in the energy use for an indoor farm versus, say, the energy used to truck that produce across the country? If I grow my lettuce in a plant factory with no natural light, it's going to cost me about 20 to 30 cents per head of lettuce, or per lettuce plant. So roughly about per pound of produce, it's going to cost 20 to 30 cents of that for energy, for light. That light energy will produce about 8 pounds of carbon dioxide just to grow that 1 head of lettuce. How does that compare to me shipping that head of lettuce across the country? So for field-grown lettuce, probably grown in California or Arizona, where 95% of our domestic lettuce comes from, no lighting costs out in the field, and if I ship it 3,000 miles, it still only produces 0.7 pounds of carbon dioxide. So food miles sounds good, but probably not the energy efficiency argument that you're trying to make. The final comment on waste, probably true. Fewer food miles means fewer instances of that sad sandwich that I had to deal with and told you about at the beginning. If that lettuce hadn't been sitting in a cooler on a truck and in the cooler at the cafe where I bought it, Yeah, I bet it would have looked a lot more like the lettuce that I picked 2 minutes before I took that picture back in the greenhouse just down the hall. But can that increased production, can that increase in quality offset the increase in energy use? So here again we are in Minneapolis. This is still a huge energy costs. Many of the vertical agriculture companies do grow already in greenhouses, taking advantage of that reduction in energy costs by taking advantage of solar energy. And even with more efficient lighting like LEDs in a greenhouse, energy is still the elephant in the room that, they really don't want to talk about. They want to tell you about the good things. Less water use, less land use. But we are seeing these energy costs again, and right now we're seeing the answer on the news. Can we grow indoors? And will that production offset the costs? Growers in the Netherlands, the premier controlled environment agriculture facilities in the world, the best engineers, the most experienced growers, generations of controlled environment growers are throwing up their hands and saying, energy costs are just too much. I'm not even going to plant this year. Some of them have suggested, let's just go back to the old model. We'll grow the winter vegetables in Spain and we'll truck it up to Northern Europe. We are at the same place we were 130 years ago. Back when L.H. Bailey said, you can do it, but it's not economically feasible. The few things that have made it worthwhile, the crops that we see again and again, you're probably as sick of me talking about lettuce as you are of me talking about lights. But crop choices. For premium market value, growers want to be able to get organic premiums. They do want that patina of growing locally, saying, hey, it is just down the hall or down the street. Indoor growing has more options for pesticide-free because we can exclude pests and diseases. We can produce with fewer chemical pest controls. So a premium market value is essential. It must be a high-value crop. You also want crops that have high production volume, things that are short, so you can fit them into multiple rows and grow 10 or 20 or 30 layers in one building. Things that are fast-growing, so you have a high turnaround. So these lettuces were started as transplants. They probably all started together on one tiny tray, off in a side room where they were lit, and then they get spread out. So they'll grow for maybe 4 weeks in that tiny tray, and then after transplant, it's another 4 weeks in these hydroponic troughs, and you're on to your next crop. You're not waiting months for your potato or your pepper harvest. So short, fast-growing, and also highly perishable. So things that the quality decreases significantly with transport or a long storage time. That leaves us with this list of crops that we primarily see in these vertical agriculture facilities. Leafy greens, herbs, microgreens, things with a very fast turnover. Tomatoes, cucumbers, peppers, strawberries, things with a very high value. And medicinals. Really, a lot of the development over the past 30 years in LED lighting efficiency is thanks to the cannabis growers. Needing, because they were only growing indoors so that they could potentially hide their crops, but growing indoors and needing efficient lighting systems. There's one other crop that's actually really, really well suited to vertical agriculture, but it's not on this list. It also wasn't in that Berlin model, which kind of surprises me because it's been growing in controlled environments for over 200 years. A crop that is short, has a reasonably fast turnover, and needs very little light. Light is not essential, but it is helpful. but the amount of light that you or I would be comfortable with, the light a little more than in this room. So very low energy costs. With my students, we are growing mushrooms this year in my controlled environment food production class, because it is a controlled environment class. Now, this is a new thing for me. I've only ever grown vegetables and fruits in the greenhouse or ornamental plants. So adding mushrooms has been a little bit of a learning curve for myself. But it's actually turning out to be a very good exercise for all of us. But mushrooms have been doing controlled environment agriculture and vertical farming since the early 1800s, when French growers first realized that they didn't have to grow these outside in fields. They could just put them in abandoned mines or caves, and they would be perfectly happy. And since then, much of French mushroom production and the majority of US mushroom production since about 1865 have been in controlled environments, a lot in Pennsylvania, to be honest. So a high value, highly perishable crop, very well suited to vertical agriculture. Where does vertical agriculture make sense? So those are what crops make sense for vertical agriculture. Where does it make sense? In places where some resources are scarce. Been hearing all week on NPR radio stories about water shortages out west. It's been going on for years. It is really coming to a point. But 95% of US lettuce is produced in California and in Arizona, places where water is extremely limited. So why not grow indoors in hydroponic systems, use 95% less water, and you could still produce that lettuce much more energy efficiently than you could in a vertical farm in Wisconsin or Minnesota. Also, in that same area, maybe they're water scarce, but they are sun rich. So renewable energy is a more sure thing there. Solar panels are only about 15 to 20% efficient though, so if you wanted to supplement your electrical energy, not use fossil fuels, you're still looking at needing about 5 to 9 acres of solar electric to light 1 acre of indoor farm. Less for a greenhouse, but that is sort of the exchange rate. So if you're thinking that plant factories are great, we'll save land at least, even if we're not saving energy, we're still going to be using a lot of land to light those, even if we chose to use renewable energy. So there are, hopefully you're seeing some pros and cons to indoor farm. And controlled environment agriculture, vertical agriculture technology, these are tools. The point is to make the best choice of your tools. I would recommend using a greenhouse for its energy efficiency, relying more on solar radiation than electrical, and using vertical agriculture, vertical growing whenever possible to maximize your space efficiency, because it really does and can make a difference. It's not just a science fiction story. An article in one of my trade magazines a couple of years ago summarized the benefits of vertical agriculture. The first three, controlled growing conditions with precision, crops produced year-round, and improvements in water use efficiency, these are all not just vertical agriculture. This is controlled environment agriculture in general, so really not specific to vertical agriculture. Reduction of input costs, I really don't see it, especially when you include energy in your inputs. But they do maximize the growing capacity by cubic volume, by growing up and using your space in 3 dimensions instead of 2. The final point that they made was that you could source production closer to the point of consumption. Now, that really isn't a great argument for food miles. Food miles aren't great to argue that by. We saw that you're burning a lot of fossil fuels to produce electrical energy, much, much more than you would to fuel a truck across the country. But there are some other benefits that I would add that are related to that close-to-home production. And those can include food security, So even if transportation lines go down, you may still have food production close to home. That does rely on energy, though. So if you have poor transportation, I'm not sure how sure your electrical grid is going to be. But it can also offer employment opportunities. So if you bring the production to where the people are, you can grow year-round, employ people year-round in a way that a lot of field agriculture does not. So a lot of our field production opportunities are seasonal. One of the reasons, as we said, for controlled environment having increased production is because you do grow all the time instead of just at specific times per year. So instead of bringing in crews to pick tomatoes when they are ripe, to pick peas when they are ripe, to pick blueberries when they are ripe, why not keep people around all year round and employ them in producing food for the local community? So that is really what I have. I'm happy to take your questions. And I also wanted to mention that if you want to visit the D.C. Smith greenhouse, the greenhouses are open. It's just a few blocks away from here on the corner of Babcock and Linden Drive. And the greenhouse is open on weekdays from roughly 8 a.m. to 6 p.m. And we love visitors. So if you are interested in seeing what the students are growing, you're welcome to stop by. Yes?
I noticed in your comparison of energy costs for transportation, and you were talking about pounds of CO2 produced to move the crop. In your discussion of energy crops and the energy needed to move them, talking about pounds of CO2, at no point did you talk about the CO2 input necessary to grow plants, which I'm sure NASA is thinking about in their controlled environment agriculture experiments, because they have to balance oxygen and CO2 for the sake of the astronauts.
So yes, plants are going to need carbon dioxide. I have 2 points to make about that one. Interestingly enough, so I got these data from Lou Albright, who is a professor at Cornell, very sadly passed away this last, I think, April. But he had been retired for a while, but was still coming out and talking about and writing papers on controlled environment agriculture, which was his specialty. But I got these data from him, and a different report that he made, he did address that CO2. And if you supplement carbon dioxide in a plant factory, you actually get an additional boost of growth in a plant factory or in a greenhouse. And my second point about that is, why didn't they include mushrooms in the Berlin model? Because mushrooms, as they grow, they decompose whatever substrate they're growing on. So they'll grow on like sawdust blocks. As they grow, they respire. Just like we do cellular respiration, we breathe in oxygen, our cells burn that energy and produce carbon dioxide. Mushrooms do that too, and as they are burning those sawdust blocks and using that energy to incorporate into their structures, they're producing CO2. So they could be producing CO2 for the rest of the crop production. So I really think that Berlin model missed a huge opportunity by not including mushrooms. But that just tells me they didn't really know what they were talking about.
I wonder if you're familiar with Professor Andrea Hicks. She gave a talk a couple of years ago about life cycle assessment.
I am not. What was her talk about? So you said
Her talk about was the rebound effect of LEDs, but she teaches life cycle assessment and anticipatory life cycle assessment. And interesting that you referred to Ted Tibbetts. His license plate was Spudnik.
Spudnik. He was Ted Tibbetts was the person behind Spuds in Space. We've got another question here down front, Tom.
Here you go, Mike.
Thanks. Yeah, I was wondering if you're familiar with the operation of Cedar Valley cheese up in, I think it's Plover.
I'm familiar with the company. Are they doing something with controlled environment agriculture?
Yes, they are. They're sort of combining the recycling of their waste from their cheese plant and they're using a greenhouse environment where this is done, where they decompose their wastewater, and they use the greenhouse environment to actually grow grapes year-round, which they can do.
That's great. There are a lot of opportunities, and I didn't go into opportunities for renewable energy.
Right.
But there are a number of ways to supplement energy and recapture heat. It's one benefit to rooftop greenhouses is recapturing that heat that's going to go up the top of the building anyway.
Right, and it produces so much heat that you even have the opportunity to see mosquitoes in the winter, if you,
I don't think that's a benefit,
right, yeah.
unless you're growing fish in there too, yes. We've got a question.
I'll be right there.
I know there's so much more I could have talked to, but I don't know how late you want to stay.
That wasn't fun, that was a job.
It was
I
hard
was
to
thinking
skim this
about
down.
light. In no place did I see any mirrors. I would think that with mirrors, you could double the amount of light.
Could you double the
Plants
amount of light with
or
mirrors?
solar light, you could have mirrors above the building. or whatever.
So there has been some effort to use mirrors or fiber optics to bring solar light further down into buildings, but the gains really aren't that great when you look at the energy levels. So to our eye, light looks so bright, but to plants, it's very, very different. The amount of light in here, like I was saying, a typical office building is, say, 50-foot candles. That's a typical architectural measure. That amount of light was equivalent to the 2 watts per meter squared that the plants were getting in this room, or would be getting in this room. And when you compare that to the 1,000-foot candles of a typical greenhouse, 2,000-foot candles of a typical greenhouse, fiber optics just hasn't been able to transfer the energy that plants need. It has worked for illumination, but as I said earlier, plants and humans perceive light very, very differently. But there are people interested in that, but it simply has not had the effect that more energy efficient lighting has done.
I've seen biofuel experiments and pilot projects with algae grown by light. What, if any, options are there for algae for food?
Algae for food? Well, there are already. So corn, Quorn, is a fungal mycelial product. So it's not actually algae, but it's a similar idea. It's a mycelial fungi. It doesn't produce mushrooms, but it's just these big fibrous mats that are converted into a chicken substitute, I think. So I think that's certainly a possibility for controlled environment production.
Other questions? Mike?
Yeah, this is going back to the first part of your talk and also what you just mentioned as part of the Q&A. Could you enlighten me, because I've never really understood, what is the difference between candle power, foot candles, and lumens, and which are the most accurate measures of light intensity? Thanks.
Okay, so what's the difference between foot candles and lumens? The difference between a foot candle and a lumen is the difference between a yard and a meter. It is simply an imperial versus a metric unit. What I was using, and they measure not intensity, but brilliance. They measure brightness that is calibrated to the human eye. I actually brought 2 meters with me. One is a light meter. It gives a reading in foot candles or lux. And that is calibrated as an architectural measure. It is calibrated to what we see. We see light best in green wavelengths. If you've ever seen something through a night vision scope, you'll notice it's in green. Mm-hmm. We see more shades of green than any other color. That's why that one was chosen. Plants, on the other hand, they don't see light the way we do. They're not interested in reading a newspaper. They want light for energy. And photosynthesis, which is directed by chlorophyll within the plant, chlorophyll is that green pigment. And if you understand how we see things, what we see is actually reflected light. So when green light hits the green leaf, it gets reflected back, the other colors gets absorbed, and we see the green light. That's why we see a leaf as green. So what that kind of tells you is that plants aren't using a lot of green light. They're reflecting it back. So if my light meter is measuring what the human eye see, it's calibrated specifically for green, yellow, and orange light mostly, which are big gaps of what the plant is actually using. So the other meter that I brought is a PAR meter, photosynthetically active radiation. It is calibrated to look at the wavelengths of light as a plant might see them, for the ones that it is most interested in for photosynthesis. And chlorophyll works best in the red and the blue range, sort of the opposite of what our eyes want. So a foot candle is not a great measure for light intensity, because that's the strength of the light, the power and energy that is provided for plants. So we really don't want to use a foot candle. I still use it in some of my materials because it's an old architectural measure, and all of my old textbooks that talk about houseplants have the readings in foot candles. What the greenhouse industry and greenhouse researchers have been trying to promote are measures in PAR, photosynthetically active radiation, measures of energy. Watts per meter squared and micromoles per meter squared are the two most common readings. So that is what I reported in you. And I actually went through, one of the last changes I made to my slides was changing from what I had written in foot candles and redoing those measurements in watts per meter squared, because I really did want to reinforce the energy importance of light to plants. And it's really weird for us to think about because we see light in a completely different way, and it's hard to think in a different way about light, but it's terribly important to how plants grow and how we are going to grow plants if we want to grow them well, whatever the situation, especially indoors.
Candle power, what's that?
Okay, so candle power is related to foot candles, and I missed that whole first part of your question. So what is candle power, what is foot candles? A foot candle is a very literal measurement. It is the brilliance, the brightness of light 1 foot away from a candle. So candle power is basically how many candles do you have in a room. It's an old physics definition from back when candles were the way that we lit things. Yes?
How many hours a day does the greenhouse light, and does it matter by crop? How many hours a day?
How many
you're
hours a
using?
day, and does it matter by crop? It absolutely matters by crop. So the most light that we offer, lighting 24 hours a day is difficult for many crops. It actually confuses them because plants can tell what time of year it is based on the day length, just like it's getting dark earlier outside. So depending on the crop, if I am growing, say, alfalfa or corn, and I have that in one of my greenhouse, I might give them 16-hour days. So the lights will still be on till 10 o'clock at night if you drive by the greenhouse. So in that greenhouse, I'm trying to replicate summer sun, bright light during the day and long days. I also have poinsettias and chrysanthemums growing. They also need bright light, but poinsettias and chrysanthemums naturally bloom in the fall when the days get shorter. So I'm turning the lights off at 4 or 6 p.m. for those crops, and I'm also pulling a sheet over them to convince them that it's dark outside because there's light bleed from all the other greenhouses, and that would confuse them. So I'm excluding light in order to get those plants to flower. It's really spectacular when I do it in the spring and you have poinsettias and chrysanthemums blooming for Mother's Day. But that's the benefit of a controlled environment, that optimum control and that precision control.
Any other questions? If not, thank you very much. This is great.
Thank you all for your attention.